Good afternoon and welcome to Carlum Cymru sessions. This session will focus on Physics Year 12 Dynamics at AS level and will be presented by Mr. Ridd from Cynvig School in Bridgend. The session will last around 45 minutes where the teacher will go through the relevant subject content. And if you have any questions, please use the question and answer section and we will endeavour to answer your question during the session. The session will be recorded and the recording with any relevant resources uploaded to the e-sgol website in the Carlum Cymru area. And without further ado, can I introduce Mr. Ridd?
Thank you very much, Mrs. Owen. Right, so we're going to be doing AS Physics Dynamics today, which I believe is the third topic in Unit 1. It's largely centered around Newton's laws of motion. Today we're going to be covering all this content, hopefully. So we're going to look at Newton's third law of motion, free body force diagrams, Newton's second law. Then we're going to look at momentum, and in particular how momentum relates to force, and then finally looking at the conservation of momentum principle. So the story of our understanding of forces goes back an awful long way. I'm not going to bore you with all of it, but it might be worth just having a quick recap. For a start, Aristotle and those great Greeks, they were the first to actually even start thinking about big questions. And they believed that some objects sort of wanted to be a certain way. They wanted to be still, for example. Some objects wanted to be moving, which wasn't a bad idea just to get us started. Galileo, you may have heard of him, obviously more famous for his work with telescopes, or inventing the telescope, the refracting telescope in 1609, but famously as well did an experiment with large masses and proved that heavier objects don't necessarily fall faster. If you were to ask most people, they would say that the heavier the object is, the faster it will fall. And that's not strictly true. That's more to do with air resistance and how that interacts with the weight of an object. He was the first to sort of understand and make that distinction and come up with the idea as well that objects wanted to continue moving in their current state. Then Newton, taking those ideas on board, came up with his laws of motion, and in particular understanding that inertia was a very important property that objects had, and that in fact the only reason why things seemed to slow down, balls stopped rolling, etc., was to do with the fact that there were external forces present that were causing that to happen. And what he acknowledged is that the natural state of objects is for them to continue doing what they're doing. So that concept of inertia, this is a slight recap of key stage 4. It's a measure of how hard it is to change an object's current state of motion. So if you think of a bowling ball rolling on a relatively frictionless alley, it will continue to roll for quite some time. As you can imagine, if you had a really long alley, it would take a long time for that ball to slow down. That bowling ball, because of its mass, has a certain amount of inertia. And similarly, stationary objects, they have a certain resistance to change in their state of motion. So it's a case of objects in motion and stationary objects. This concept of inertia, the idea that objects want to continue, really, or how hard it is to change an object's current state of motion. So what we realize is that objects that have a large amount of inertia also have this property of having a large mass. And to change the inertia of a large object is very, very difficult just because of the amount of mass that it has. So what is a force? Well, it's quite an abstract concept, what a force is, really. And I guess the best way we can describe what a force is to think about how it affects objects. And in particular, a object which experiences a force will either have a change in its velocity or it will change the direction of its motion. So in thinking about what a force is, it's better to conceptualize it as what it does to objects. Like I said, it will either change an object's velocity or change its direction, which is pretty much saying the same thing. So like we said, inertia is all about mass. And the law of inertia can also be often quoted as Newton's first law, and that if there are no forces acted upon an object, or if the forces are balanced, which is more commonly the case, okay, that forces are balanced, then it will remain stationary, or it will move at a constant speed. Now, you notice I've underlined the or there because it can't be both, okay? And given any question, you're going to have to consider what outcome you're going to go for. Is it stationary or constant speed? Now, you should know by now that force is measured in newtons. And I suppose if you do something incredible in physics one day, you bright, smart people, then maybe you'll have a unit of measurement named after you. Wouldn't that be nice? So, some basic examples then. If we've got two forces that are balanced in this case, right, there are two balanced forces, then this object would be stationary, all right? This book would be stationary, forces are balanced. Now, in this situation, we've got a rocket, we got weight and drag force backwards, we've got thrust forwards. But I've put this little statement down here, look, okay? I've said that the weight plus the drag is equal to the thrust. So in that case, the forces, we would say, overall are balanced, and the object is moving at a constant speed. Now, why constant speed? Well, it's all to do with this drag force. If there is drag force present, okay, if drag is present, all right, constant, well, or an object, more importantly, an object must be in motion. You can't have a drag force or frictional force for an object rolling, for example, without that object being in motion. So here we've got an astronaut in deep space. You notice I've done no arrows. There were no arrows acting on this astronaut. He's in deep space. He might be in a lot of trouble. Who knows? And in this situation, stationary constant speed, well, I don't know. Depends. It depends. I mean, what Einstein would argue is anything actually stationary? I'll let you think about that, but maybe we're going a bit too deep there. Okay, the racing snail here, if we've got forces in different directions here, well, they can still all be balanced. Look, as long as reaction is equal to weight and force is equal to friction, then yeah, the forces are balanced. We've got them off at different angles here, but that's still fine, and this would be moving at a constant speed. All right, let's see now. Let's move on. Oh, what's happening here? Okay, so here's an example then of two forces. We put numbers to them now, right? So if I had a jet ski, it's 2,500 newtons forwards and 2,500 newtons back. We're going to define something called the resultant force now. The resultant force, I would say, is equal to 0. And the resultant force is simply the sum of all forces. You might have seen that annotation a couple of times. The sum of all forces. If we were to add those two up, we don't get 5,000. We have to appreciate that these are vectors, and as such, they are in opposite directions, which means that they will have a vector sum of 0. The resultant force will be 0. So yeah, Newton's first law applies. This is Newton's first law, and of course that means we've got constant constant velocity. Right, moving on. Newton's second law comes straight off the back of that then, really. And if, in fact, you don't really need two laws for Newton's laws. The second law actually encompasses the first, all right? But anyway, what happens if the forces are unbalanced? So now, look, he decides to speed up because, you know, he's having a good time. It's jet skiing, for God's sake. So now, if we were to define the resultant force, which is often given this notation, F subscript R, we would say 7,000 minus 2,500, and that is equal to 4,500 newtons, okay? And we'd maybe go a little bit further. We'd specify a direction as well. We'd say, you know, to the left. And this would also cause now an acceleration in that direction as well. So Newton's second law tells us, first of all, that an object, if the forces are unbalanced, then we'll get an acceleration in the direction of the remaining force, or the resultant force in this case. And that acceleration then is going to be proportional to the size of that resultant force. All right. Oh, I forgot I did that. So it's another example of Newton's second law. You've got two guys in a tug of war. Who knows why? Bit of a Squid Game scenario maybe. And then you can see here clearly that, I don't know, this guy here, he's had his Weetabix. So here we can see there's a resultant force once again of 250 newtons to the right. So this will cause then, of course, an acceleration in that direction. And then, of course, your man here, okay, fighting for his life, okay, he manages to put in a huge effort. And again, now we've got a resultant force, but this time to the left. But despite the fact that we have got an acceleration to the left, one of the things you need to appreciate here now is that one of these is going to cause a larger acceleration. It's quite obvious which it's going to be. It's the one with the larger resultant force, okay? And then again, if they're both put with the same amount of force, Newton's first law applies here, and we'd be stationary yet again. So which has the greater acceleration? Why? Well, if you look at these two cars, this one's got a very large mass. This one's got a much smaller mass. So F1 cars can, you know, weigh, I think it's about 600-700 kilograms. They're pretty light, okay? Whereas a large family SUV might weigh as much as close to 2 tons, okay? So mass certainly affects the rate of acceleration. And of course, the other thing is the amount of force that the engine can provide, okay? Of course, in a Formula 1 car, they've got a huge amount of force being produced by the engine. And Newton's second law, you'll have seen written like this. A is equal to F over M. Listen to the equation. The equation is talking to you. It's telling you something about the nature of reality. It's telling you that the amount of acceleration an object will possess is directly proportional to the force applied to it, or the resultant force, maybe we should say, and inversely proportional to the mass. All right. So if you want your car to go faster, take all the seats out. Don't do that. Right, Newton's third law then. So we've done Newton's first two laws. We'll do some calculations and stuff in a moment. We'll look at some past book questions. But on to Newton's third law. How does the moon stay in orbit around the Earth? Well, I'm sure a lot of you are screaming at the screen now and saying, yes, well, that's gravity. And you'd be right, of course, okay? But does the moon exert a force on the Earth? We said, right, well, the moon is held in orbit about the Earth by the force of gravity, but does the moon have a force of gravity acting on the Earth? I don't know what you're saying there, but some of you will be saying yes. And I've got another question for you. Which force is greater? Well, you might, if you weren't a physicist, say, well, I think that the force of the Earth on the moon is greater because the moon goes round the Earth, and that's quite a common misconception. But we have to remember Newton's third law. For every force, there is an equal and opposite reaction force. So what does that mean? Well, it means that the force of the Earth, all right, pulling on the moon is got to be the same as the force of the moon pulling on the Earth, all right? And then you might be thinking, well, how is it then that the moon goes around the Earth? Well, again, now it's all to do with mass and the difference in mass. Let me give you another example, okay? If I have a cannon and I'm firing a cannonball, Newton's third law tells us that if the cannonball experiences 8,000 newtons of force, then the cannon will experience 8,000 newtons of force. Now, why doesn't the cannon shoot back as fast as the ball? It wouldn't be much good, would it, as a weapon if the cannon shot back as fast as the ball, because that would make the cannon just as lethal as the cannonball itself. And the operator would be obviously just as likely to be injured, right? So the difference, of course, is the mass. Because this has a very large mass and this has a much smaller mass, because acceleration is force divided by mass, and acceleration is force divided by mass, little mass, okay? Then you can see that the acceleration for the cannon here would be much smaller than the acceleration from the cannonball, because, of course, even with the same force, look, it's the same force, that's what Newton's third law states, because of the smaller mass of the cannonball, we have a much higher acceleration as a consequence. Therefore, meaning that the ball will be moving a lot faster than the cannon itself. That's how recoil works. Some examples of Newton's third law. Well, first of all, actually, before I just crack into some examples, I think this definition is better than the one that Newton just gave us. Okay, sorry, Newton, no disrespect. If object A exerts a force on object B, then object B exerts an equal and opposite force on object A. The reason why I say this is a better formula or better definition to use is because it's a little bit more exam friendly. And in an exam, if you're asked to state what's the Newton third law pair, for example, then if you think about any problem in terms of two objects and you identify what object A is and object B is, then you can state it in very clear terms. I'll give you an example. If I push the boat, if I step off the boat and push the boat backwards, then the boat pushes with an equal and opposite force and pushes me forwards. Think about a speedboat. You know, I couldn't remember what that was called then for a moment. The speedboat, right? A speedboat, the propeller, you think of the propeller at the back. The propeller is exerting a force on the water. So you think about object A and object B, right? Propeller will say is object A, and the water is object B. So in terms of Newton's third law, what we'd say is that the propeller, object A, exerts a force on the water, object B, and then the water, object B, exerts an equal and opposite force on the boat, object A, pushing it forwards. Okay, so that's why the boat accelerates forwards or moves forwards. Think about it, right? For the boat to have a force forwards, it has to push water backwards, right? That's it in simple terms. Same with the skateboarder, right? For him to get a force going forwards, he has to push the floor backwards. So the skateboarder pushes the floor backwards, and the floor pushes the skateboarder forwards. There we've got object A and object B, equal and opposite forces. Other things about Newton's third law then we have to sort of bear in mind are that any Newton's third law pair, like the ones we just discussed, have to be the same type of forces as well. So for example, you can't have a Newton's third law pair between a gravitational force and an electrostatic force or a contact force. Any Newton's third law pair has to be like for like, and they have to be along the same line of action. Okay. Right, free body force diagrams. Now, this is incorporating some of Newton's third law as well. Here we have a block on a slope. You can see the Newton's third law pairs here. Let's have a little look at them. So you got the weight of the block, which is really the force of gravity acting on the block from the Earth. And then the Newton's third law pair for that, look, is the gravitational force on the Earth by the block. So just as a simple example, if a skydiver jumps out of a plane, then there's a force of gravity pulling him downwards, or his weight, we should say, as physicists. That weight is the force of gravity from the Earth acting on the skydiver. But the Newton's third law pair for that situation is the force, the gravitational force that the skydiver exerts on the Earth. So there is this equal and opposite force of attraction between the two. Here we've got a contact force, okay? If you're standing, right, on the ground, then you're exerting the contact force on the ground, and the ground exerts an equal and opposite contact force on you. That's providing, of course, you're not standing on thin ice, in which case it might not push back with enough force, and it's sad times right there. So you've got friction on the block, okay, the friction on the block resisting its motion to go down, and then you've got the friction on the surface, which is the equal and opposite force there. Gets a bit complicated, there are lots of arrows. So very often we simplify free body force diagrams into just the forces that are acting on that object, just to make it easier to understand. And there we've got the three forces acting on that object, okay? Now, the reason I put the incline or the block on a slope thing in is because it does pop up a lot. It pops up in past paper questions with kids going down slides or sledging or skiers. It pops up as well, yeah, with just objects, you know, and the frictional force that will cause them to slide, or even with something called toppling, which you'll have done when you did moments, not moments, when you did, yeah, when you did moments, okay, and centre of mass. So here's some of the physics involved and the forces involved in a block on an inclined plane, as we got here. So the first one where we start here to think about this situation is we've got this force downwards mg. And what we're going to assume for this now is that this block is in equilibrium. And by that, I mean all the forces are balanced. Maybe we'll say it's stationary, okay? So you've got weight downwards. Weight is never anything other than downwards in these diagrams, okay? It's always towards the center of the Earth. But this weight then is going to have two components. If you think about going sledging as an example, right? When you're on a sledge, the steeper the slope is, the faster you go, or the more you'll accelerate. And the reason behind that is just to say that from a physics point of view, the steeper the slope is, the bigger the component of your weight will be acting down the slope, which is what we've got here, right? So if you label this up, you actually find out that, you know, this is theta, all right? And if you remember what we did on resolving vectors in a previous video, then what we can say is that this vector here, right, this mg, will have a component which is perpendicular to the slope of mg cos theta, and a component which is parallel to the slope of mg sine theta, all right? And then as well, in some of these problems, you can make some rational arguments, right? Because if Newton's first law applies, right? So if this is in equilibrium here, all right, then we'd have to say that Newton's first law applies. Then we could say that mg, so we're looking at things which are perpendicular to the slope now, mg cos theta, this force here, must equal n, which is known as the reaction force. All right, sometimes it's normally it's r. I'll write it down as r. Then we could also say as well that that would be sort of perpendicular to the slope, and then parallel to the slope, we would also be able to say that mg sine theta is equal to the frictional force, providing that this system is in equilibrium. So you might have to start thinking about, you know, Newton's laws and these free body force diagrams, okay? It gets a little bit more complicated than those ones I showed you earlier on because we have got angles involved. You do know how to handle vectors now after all. Okay, let's move on. So I'll give you another example, right? So you could have a paraglider. And I don't know if you've seen paragliders. These guys, they hold on to a thing which is attached to a boat. Give the boat, it's not great, is it? Okay. There we go. There we go. That's very good. So you'd have maybe a free body force diagram. Let's say he's moving right this way, all right, at a constant speed, right? He's traveling with a constant speed v this way. So if he's traveling with a constant speed, we know then that Newton's first law applies and all the forces are balanced. Now, what forces would be acting on him? Well, we'd have his weight downwards. I said downwards. That's not very down, is it? Let's try again. Okay, let's try again. There was weight. There we go, that's better. Weight downwards, which is mass times gravity. Okay, good. We'd have some kind of drag force, D, okay, backwards. All right. And we'd also have, as well, some kind of lift force, all right? Some kind of lift force L, potentially. Now, this could all be, for example, an angle of theta, all right? And then, of course, we've got this tension force, T, as well. So you can see there's a lot to resolve here, really. And you might have to say something like, well, horizontally here, we'd have to say that T cos theta, which is going to be this here, T cos theta, would have to equal the drag force. And we'd have to say then that mg as well, this is the vertical one, equal to the lift. So we get all different kinds of scenarios here, all right? But there's a little bit more to it than that, look, okay? Because not only have we got mg downwards, all right, but also, look, we've got this component of tension downwards. So we'd actually have, let's see if we can delete this a second. Oh, strange. Pen has decided to do some crazy things. Okay. So we actually have, in this situation, a little bit more complicated. We have mg downwards plus t sine theta. And that would equal L, okay? Because there would be also plus t sine theta here. So, yeah, you know, given the situation, you might have to construct these little equations, all right, so that you're able to sort of resolve the vectors and work out the forces, okay? Right then, onwards now to momentum. So we're going to start off by looking at the conservation of momentum principle. Well, I suppose we should start off with this equation. Momentum is simply mass times velocity. You can think of it as how much inertia an object actually has, right? And yeah, if you think about an object which is massive, moving fast, and it's got a lot of momentum. As simple as that. Conservation of momentum principle though, is very, very important in physics, okay? It's one of those fundamental principles that we hang everything on, okay? Without this, you know, being true, then physics kind of falls apart. So the conservation of momentum principle then simply states that the momentum before a collision is the same as the momentum after a collision, as long as there are no external forces acting on the system. Okay, so if you look at this simple example here, if we've got this thing's stationary, right? This is stationary to begin with, and if we had this smaller mass colliding with it, then the momentum before in the whole system, that is, mind, right, would be m times u. The larger mass there, the blue one, has no momentum because it's not moving. Because remember, if it's stationary, its velocity is 0, so it has no momentum. Now afterwards, whatever the product mu is, all right, mu, whatever the product mu is from here, look, okay, that would have to equal the momentum afterwards. In this case, it would be m times big V, which is the momentum of this, minus m times little v. Now you might think, why minus? Well, we have to remember that momentum is a vector quantity because it's defined with a scalar times a vector, m times v. It is a vector quantity, so the direction matters. Right. Yeah, so the momentum before would have to equal the momentum afterwards. Right then. So have a look at an example of, let's just take a look at an example here, right? So let's imagine we have a bull. This is my fast live bull. This is, I think. Oh, I'm not sure about that bit. Hang on. Big tail, fluffy tail. There we go. And do you know what? I'm going to give him another leg as well. You know what? Yeah, got that. That'll do. That'll do. So there's my bull, and let's imagine that he's up against a bullfighter. Okay. And let's imagine that the bull's got a mass of 1,200 kilograms. Let's imagine the bullfighter's got a mass of 100 kilograms, quite a big guy. And let's imagine the bull's moving at 10 meters per second. All right. Now, this is the situation before. All right. And then after, all right, after, we'll imagine that the bull, okay, because we want the bull to win, don't we, ultimately? All right. Oh God, I've got to draw another bull now. I regret this. I regret it. Okay, that'll do. Imagine that after, okay, this we've got this situation. Because bullfighters are fundamentally bad people, so we don't want them to win, right? So now, after that collision, so this would be before, all right, and this would be after. So after the collision, we imagine that both objects are stuck together, okay? And we can actually do the math now and work out, right, what this velocity will be. What will this velocity be? So before we know what the situation was, we know that momentum is conserved, and we can use that principle to work out what the velocity of the, if you like, the bull-man system will be. So we'd say that before we had 1,200, look, which is the mass of the bull, times 10, so that's m times v, all right, plus the momentum of the bullfighter, which was 0, because he's not moving, And that's going to equal the momentum afterwards. Now, the momentum afterwards, let's see. Well, now, look, you've got the man and the bull, they're just like one system. So actually, the mass of this afterwards would be 1200 plus 100 times our unknown velocity v, all right? And then you'd end up with v is equal to 1200 divided by 1300, and that's equal to 9.2 meters per second, all right? So you can see here now that the bull slowed down in that collision, all right? And that's just one example. I was going to do another one, all right? But actually, I think given the time, we'll just move on, right? Now, there are scenarios as well where objects move off after collisions, okay, in opposite directions, all right, for example. And then you have to remember that this momentum is going to be negative, all right? We're going to have a negative momentum here, and these are positive momentums, like so, all right? Right, deriving Newton's second law from change in momentum. So this is something that you're expected to do as part of your course, okay? And what we've got to remember are two equations, right? Remember that A, this is one of the equations of motion, is equal to V minus U over T. Hope you remember that one, all right? We also know as well from Newton's second law that F is equal to M times A. What we're going to do is combine these equations. I'll call this one 1, if you like. I'll call this one 2. And we are going to sub 1 into 2. And if we do that, we end up with F is equal to... Right, now I'm going to write down the M. And then instead of A, I'm going to write down B minus U all over T. Then I'm going to expand that out so that it's MV minus MU all over T. And really, if you look at it, MV minus MU, well, V standing for final velocity, U standing for initial velocity. What this is final momentum minus initial momentum, which is the same as saying the change in momentum over time. And really, we can consider force, right? Yes, F equals ma, we've got Newton's second law, and that's fine. But maybe a better definition, or a good definition for what a force is the rate at which an object's momentum changes. All right, that will tell you how much force is being applied to it. You may well have to derive that equation, so be ready for it, okay? Now, that brings us quite conveniently, okay, to the end of that little section. And really, we've completed all of the things in our checklist. I'm going to jump straight into now looking at some past paper questions, okay, on this. We've got about 12 minutes left. So the forces acting on a hailstone even, falling in a horizontal crosswind can be represented in the diagram. Calculate the magnitude and direction of the resultant force acting on the hailstone. Well, to do that, look, we'll first resolve these two vectors, okay? First thing we'll do is resolve these two vectors. And if you think about it, the resolution of these two vectors is going to be 2.0 times 10 to the minus 4 newtons. Because they're all, in the same direction, really. Well, in opposite directions. We can just sum them up, okay, really quickly. And then what we end up with is a free body force diagram, which looks a bit like this, okay? We've got 2.0 times 10 to the minus 4. And we've got 5.0 times 10 to the minus 4. Now, if we want to resolve these vectors, we want to add these vectors together. And again, this was all included in the previous video. And what I need to do is add these two vectors together, point tail, so that we end up with 2.0 times 10 to the minus 4, 5.0 times 10 to the minus 4. And then the resultant So done better there. But the resultant is going to be whatever causes that shape. So we can use old Pythag here to work out the magnitude of that resultant, and that's going to be, I just going to leave the things off for now, 5 squared plus 2 squared, okay? Now x here with the 5 squared plus the 2 squared, just get to my answers a second. Comes out as 5.4 times 10 to the minus 4. And don't forget now, it says magnitude and direction. Read the question very carefully. So if you've drawn a little diagram like this, so helpful. If you've drawn a little diagram like this, an examiner is going to know exactly what angle you mean. All right. You get a couple of options here. You get tan theta. The tan theta is going to be 2 over 5. All right. I've left off the magnitudes there, okay, because it'll work out the same anyway. All right. And then you get the theta is 21.6. All right. Okay, good job. At a later time, the wind has stopped blowing and the hailstone falls at terminal velocity. In terms of forces, explain why the hailstone is at terminal velocity. Well, terminal velocity happens, or I feel like you could say that, you know, terminal velocity, terminal vel, is constant speed, isn't it? All right. This happens because, in this case, the air resistance now eventually, which is always a good word to use here, equals or balances the weight. So in other words, when the vertical forces are balanced, okay, you could say that the resultant force is equal to 0, okay? Right, yes, so when the drag force, when that this force here gets larger, then it will balance and then it will be moving at a constant speed. Remember, drag force is proportional to velocity. So as that hailstone gets faster, the drag force will get larger. That's why cars have a top speed as well, okay? You know, they've got a certain force of the engine, they accelerate very rapidly to begin with. But of course, the faster they get, the greater the drag force becomes until it eventually balances the driving force, and then the car's reached its top speed. Diagram shows a roller skater being pulled along a horizontal road at constant velocity. Lazy guy. The total resistive force to the skater's motion is 40 newtons. Show that the tension T in the dog lead approximately 50 newtons. Well, let's see now. We know that if he's moving at a constant speed, we know that this component here must also be 40 newtons. And we know that this is 36 as well. All right, just by doing a little bit of parallel lines and angles. So what that means is that T, all right, T cos 36, all right, T cos 36 must equal 40, which is that horizontal component, isn't it? So then T is equal to 40 divided by cos 36, okay? Which is, I think it is equal to something like 52, I think it is. No, 49, yeah, 49.6, 9.6. Later, the roller skater moving the same velocity as in part A extends the dog lead as shown in the diagram below. Assuming that the tension T is the same as in part A, explain why the roller skater initially accelerates. Well, this would be a case of having a larger horizontal component of force. Because if this angle is smaller, okay, if this angle is smaller and the tension stays the same, then there'll be a larger horizontal component of force causing them to accelerate more. All right. That one next one's easy. The acceleration. All right, well, A is equal to F over M. Okay, great stuff. We know as well here that if I do, let's see, if I do T cos 20, all right, then that comes to yeah, that comes to 46.4 newtons, okay? And then, of course, because that 40 newtons is backwards, so we've got 46.4 newtons this way, we've got this 40 newtons backwards, and that means that the resultant force here, okay, is equal to 6.4 newtons, and therefore the acceleration, which is what we're after, is 6.4 newtons divided by the mass, which is 35 kilograms. Now, remember, it's always the resultant force you're using to work these things out, always the resultant force, which in this case then produces an acceleration of 0.18 meters per second squared. All right. The last one's on work done. I'm going to leave that one for now. I'm just going to do this one real quick, I think, because it's based on what we talked about earlier on. Boy on a sled, read it at your own leisure. On the diagram, the arrow represents the total weight of Matthew and the sledge. Add 2 more arrows to show the normal contact force, always perpendicular to the surface. All right, I'll label that N for normal contact force then. And the frictional force on the sledge. Now, the frictional force will be back here. Okay. Whoa. Excuse me. The frictional force is going to be back here like that. Okay. So, we've done everything in that. Show that the component of weight parallel to the slope is approximately 200 newtons. So the component of weight parallel to the slope here we're after, and we're going to show that that's 200 newtons. Well, we will also have, look, a component here, all right? Now this one's going to be W cos 20, because this is 20 as well. And this one here is going to be W sine 20. So W sine 20 is what we're after. Now W, the weight, is mass times gravity, which is 62 times 9.81, okay, which is equal to, oh, I tell you what, I'm going to skip straight ahead, right? So I'm going to do 62 times 9.81, right? That's going to be his weight, so that's W, all right, sine 20. And that equals, well, pretty much it's approximately 200 newtons, okay? So we work that vector out there. And then, let's see, calculate the magnitude of the normal contact force. Normal contact force here then, which is N, okay? N is going to be equal to W cos 20, all right, which is the other one, which is significantly bigger. And the last one, well, that's a SUVAT problem. Maybe you have a pause, right? If you've watched this, then maybe, because I think we're at the end now, maybe you could use this formula, okay, which is one of your equations of motion, to solve that last one, all right? Okay, I think we're pretty much at time now from what I can gather. I hope that some of those past paper questions were clear enough, and I hope that you feel like we went through enough on Newton's laws there. By all means, watch it back at your own leisure, and yeah, that's me done, I think.
Thank you very much, Mr. Rydd, and for a synopsis of dynamics and Newton's laws. Thank you.